Okay, so here is our last video for the material on the complex number system. In this one we're going to look at powers and roots. So the idea here is to understand how, why do we actually go to the trouble of writing a complex number in polar coordinates? What's the advantage of doing so? What we're going to see is that certain calculations that might be difficult or in some cases impossible in the usual rectangular XY coordinates, they become quite simple simply by a change of coordinates, by a change of perspective. So the first one is to think of as computing powers, so integer powers of complex numbers. So think about computing something like z to the n, right? So, what are you going to do in rectangular coordinates? I guess you would do like a plus I times b, a plus I times b, right? You multiply by itself n times, and then you expand and you expand and you expand and you expand, and that's a huge mess. Or maybe in the best case scenario, you remember your binomial formula, and you're like, okay, I know that there's a formula. It's a to the n, and then it's n times a to the n minus 1 times ib, and then there's like an n times n minus 1 over 2, and there's an a to the n minus 2 and an ib squared, and a whole bunch of other terms, and then you got to deal with the fact that there's powers of I showing up in there, and so there's a lot of work to kind of, still you've got to kind of do some work to simplify that thing. It's not going to be a pleasant calculation, except, maybe if n is equal to 2 or 3, it's not so bad. But for higher powers, it's going to be awful. What about in polar coordinates? So in polar coordinates, I take my complex number z and I write it in this form, r e to the I theta. So remember here that r is the modulus of z, right? It's the square root of x squared plus y squared. And remember that e to the I theta satisfies cos theta plus I sine theta. So if I want to do z to the n, so this is r e to the I theta raised to the nth power. So you kind of do the obvious thing. In this first step, it's not one that we've proved, but you can check the textbook if you want to. Some of the details are in there. You can distribute that exponent. You can write it as r to the n times e to the I theta to the n. And now remember that de Moivre's theorem says that, well, e to the I theta to the n, we can write that as r to the n times e to the I n theta, right? So if we know the values of r and theta, right, now r to the nth power, remember r is a real number, so this is just a real power. R to the n is just a real power. And here we're just doing a multiplication. We're taking whatever the value of theta happens to be, we're multiplying by this power n. So we just have to do a multiplication. And then if we wanted to convert back into rectangular form, we can use the Euler identity again, and we could write this as r to the n times cos n theta plus I times r to the n times sine n theta, and we're back into rectangular form. And so in many cases, this method for computing powers is much, much easier than working with rectangular coordinates. So as an example, let's say we want to do 1 plus I. We want to raise this guy to the 5th power. So what do? So first step is you got to convert this guy into polar form. So what do? So we say, okay, so z is equal to 1 plus I. So the modulus of z is going to be the square root of 1 squared plus 1 squared is the square root of 2. Now, here's what you can do. If you have z is equal to x plus iy, and you want to figure out the argument, you don't necessarily want to go through the whole tan theta equals y over x thing, because then you got to remember values for tan theta, and you probably don't. So what you can do is you figure out the r value, right? So here's your r value. And you factor it out. So if you multiply and then divide, of course you haven't changed anything. So you can write things like that. And the reason you want to write things like that is that this number that's left over is something that's going to have modulus 1. So this x over r, right? That's your cos theta. Y over r. That's your sine theta. And sometimes you get lucky and you can recognize the numbers as ones that you're familiar with. So here I pull out the root 2 and I write this as 1 over root 2 plus I times 1 over root 2. And then I recognize 1 over root 2. I recognize this as, the values for x and y corresponding to theta equal to pi over 4. And so this is root 2 times cos pi over 4 plus I times sine pi over 4. So I get that 1 plus I is equal to root 2 e to the I pi over 4. And now if I wanted to calculate z to the 5th power, well, I don't have to multiply 1 plus I times 1 plus I. I don't have to do that and multiply by itself 5 times. That's going to be a lot of work. What I do instead is I say, okay, well that's root 2 e to the I pi over 4 to the 5th power. And just like on the previous slide, we say, okay, so that's root 2 raised to the 5th power, and then e to the I times, and here we multiply the angle, 5 pi over 4. Okay, so then you might have to, maybe remind yourself, where is 5 pi over 4? So there's pi over 4. 2 pi over 4 is pi over 2, 3 pi over 4, 4 pi over 4 is pi, add one more, you're down here. That's 5 pi over 4, places you in the 3rd quadrant, right? So the related angle is still the same as before, right? It's still a 4 in the denominator. It's still the same related angle, pi over 4, but the signs change. The sign for both sine and cosine, they both change in this case. So I'm done if I want to leave my answer in polar form, but maybe I want to convert back. Root 2 to the 5th, so root 2 times root 2 times root 2 times root 2, you can work out that that's going to be 4 times the square root of 2, or you could leave it as square root of 32 if you like, times cosine of 5 pi over 4 plus I sine of 5 pi over 4, and you can evaluate those trig functions. So this is going to be minus 1 over root 2, and then I times minus 1 over root 2. And if you want to push that 4 root 2 in, and you're going to get minus 4 minus 4i, right? Nice and simple. Now, you could try doing it the long way. Feel free to try doing it the long way. You'll come out to the same answer, but it's going to take you a little bit longer. And of course, well, with the 5th power, you could do it. It's not so bad. I mean, the way to do it if you're going to do the 5th power is square it first. You'll find that when you square it, it's not too bad. It squares to 2i, I think, and then square it again, and now you've got the 4th power, comes out to be minus 4, and then you multiply by 1 plus I, and you've got your answer. But now imagine that I've asked you to raise it to like the 17th power or something. You'll see that pretty quickly the polar form is going to be much nicer than working with the rectangular form when you're computing powers. Okay, so with powers, it's certainly more convenient to work in the polar form, but it's not a necessity. With enough computational power, you could compute your complex powers in rectangular form. Roots, on the other hand, you can play around. You can try doing it with square roots. Try to solve in general this equation like z squared equals w. Try to come up with a general formula for it. It takes a while. You work at it. You can come up with a formula, but it's complicated. It's ugly. And then if you try to do it for say 3rd roots, 4th roots, it's next to impossible. In polar form, however, it's pretty straightforward. So the way this works in polar form is you've got some number you're trying to calculate a root from, right? So what we're trying to do here is we're basically trying to compute the nth root of w, so w to the 1 over n, right? And so computing this guy, so this is going to come out to be some value z. We don't know what z is yet, right? So computing this is like solving the equation z to the n equals w, right? And by the way, this is a degree n polynomial. Remember that the fundamental theorem of algebra guarantees us not just one solution, but actually n solutions. So we are going to get n roots in general. We expect to get n roots in general. So how do you actually generate all these solutions? So the idea is you take W. So W is, this guy is given to you. So W is given to you. It's some particular number. So somebody gives you W, you figure out how to write it in polar form, right? And now if you're going to be working in polar form, well, you'd better write Z in polar form as well. So we write Z in terms of R and theta. So Z equals R e to the I theta, right? Where R and theta here are, at this point, they're unknown, right? That's what we're trying to figure out. And we say, okay, well, that's fine. Whatever r and theta are, we now know how to compute z to the n in terms of r and theta, right? Because z to the n is going to be r to the n times e to the I n theta. That's z to the n. W is ae to the I phi. I'm calling it phi here, so we just substitute in. Z to the n equals w. All right, fine. Now, where does the kind of trick come in? What's the punchline? The punchline is to remember that you can add any multiple of 2 pi that you want to the angle, and you're not going to change the complex number w, right? You get the same complex number for any multiple of 2 pi. So that doesn't change w, but it does change the roots, because if we now kind of solve for r and theta, think about solving for r and theta, right? So you take this, you have this equation, you have r to the n, e to the I n theta is equal to a e to the I phi plus 2 pi k. And just like if you're working in rectangular coordinates, if you have two complex numbers equal, you equate the real parts and the imaginary parts. In polar form, you equate the modulus and you equate the arguments. And so we know that you must have r to the n equal to a, right? And those are two positive real numbers. A is a positive real number. Remember, it's the modulus of a complex number, and so you can take the nth root of it, and you get the usual positive nth root. So r is just the nth root of a, the usual positive nth root. And then you also compare the arguments, and you say, well, n times theta must be, well, it must, it could be phi, but the point is it could be phi plus any multiple of 2 pi. And adding those multiples of 2 pi doesn't affect the value of n theta, but it can affect the value of theta, because if we divide by n, now suddenly theta is phi over n. You have this sort of basic angle, plus now some multiple not of 2 pi, but of 2 pi over n, right? And now we're adding multiples of some fraction of 2 pi, and that means that we are actually changing the value of theta. For each value of k that you put in, you're changing the value of theta. Until eventually you hit, n minus 1, right? That's going to be the last one where you get something different, because once you hit k is equal to n, that's going to give you phi over n plus, well, n times 2 pi over n, it gives you phi over n plus 2 pi, right? And then we know that adding a multiple of 2 pi, that's going to take us back to where we started. So all together, you notice that you do get 1, 2, 3, right? For k equals 0, that's one solution. 1 is another solution. 2 is another solution. All the way up to n minus 1. That's a total of n different solutions to this problem. Okay. So you can kind of write down a general prescription here, right? You can kind of write down a formula. I've got it here for both r and theta, but it's more interesting to kind of follow the procedure and see how things work. So here are a couple of examples. Let's say I want to solve these equations. Let's say I want to solve z to the 6th equals 1. Okay, so solving z to the 6th equals 1. So we let z equal r e to the I theta, and we note that 1 can be written as e to the I times 2 pi k, right? Because 1 is e to the I times 0, but I can add any multiple of 2 pi that I want to that. So I can write 1 as any multiple of 2 pi. So k here could be 0, it could be 1, and so on. In fact, we're going to consider multiples of k up to 5. Okay, so z to the n is going to be r to the n. Well, sorry, z to the 6th, right? We're doing z to the 6th. So z to the 6th is going to be r to the 6th e to the I times 6 theta, and that's going to be equal to, well, 1 times e to the I times 2 pi k. And so I get two equations now. R to the 6th equals 1. Well, the only kind of positive real solution here is that r is equal to 1. And I get that 6 theta is equal to 2 pi k, which tells me that theta is equal to k times 2 pi over 6. So if I simplify, that's k times pi over 3. So if I now consider possible values of k starting at 0, I get that theta is equal to, well, 0 if k is equal to 0, pi over 3 if k is equal to 1, 2 pi over 3 if k is equal to 2, 3 pi over 3, but 3 pi over 3 is just pi, right? And then 4 pi over 3, and then 5 pi over 3, right? And I mean, I could keep going, but when I get to 6 pi over 3, I'm at 2 pi again. I'm back to 0. I'm back to the place where I started. And so if you wanted to, you could write out all of these answers, right? So the general answer here is that z is going to be equal to e to the I times k times pi over 3, where k is equal to 0, 1, 2, 3, 4, 5. And you can, for each value of k, you can, if you want, you can convert these back into rectangular form. It's a fair amount of work with 6 different solutions, so I think I'm not going to do it. But let me point one thing out here. If you plot these points, all of them live on a circle of radius 1, so they all live on the unit circle, and they all just correspond to these different values of the angle. So one of the points is over here. That's the first root when k is equal to 0. So if k is equal to 0, I just get z equals 1. That's one of my solutions. I get this guy here. If k is equal to 1, I'm at the angle pi by 3. If k is equal to 2, I have the angle 2 pi by 3. I know how to evaluate that guy. If k is equal to 3, I've got the angle pi. So z equals minus 1. That's also a solution. K is equal to 4. And k is equal to 5. And notice that the roots are all kind of nice and evenly spaced around the unit circle. There's an angle of pi over 3 between each consecutive root, so you get this nice even symmetric spacing of the roots around the circle. And in fact, this is something that works in general. So let me do the other one for you, or at least get it started. We just have to add a page because we're out of room. So let's insert one new page. There we go. And let's try z to the 4th equals 16i. So with z to the 4th equal to 16 times I, okay. So here my w is equal to 16 times I, and remember that I is e to the I pi over 2. So now I've got this into my polar form, and I want this to be equal to z to the 4th, so I want this to be equal to r to the 4th e to the I times 4 theta, right? Where z is equal to r e to the I theta. So I compare these and I say, all right, so r to the 4th has to be equal to 16. 16 is 2 to the 4th, by the way. So that tells me that r has to be equal to 2. And then I know that 4 times theta must be, comparing the arguments, 4 times theta must be equal to pi over 2. But again, I can add a multiple of 2 pi here. So I could have k equal to 0, 1, 2. or 3. By the time I get to k equals 4, I'll be back to where I started with, since I'm dividing by 4. So theta in this case would be pi over 8 plus k times the multiple of, if I take 2 pi and divide by 4, I end up with pi over 2. And so that means that my solutions here, I get 4 of them. I get z0 is 2e to the I pi over 8, z1 2e to the I. If I add pi over 2, that's going to get me to, let's see, pi over 2 is 4 pi over 8, so I get to 5 pi over 8. Z2, I get 2e to the I. Add another 4 pi over 8, that gets me to 9 pi over 8. Z3, I add another 4 pi over 8, I get to e to the I 13 pi over 8. And again, if I were to plot those points on the unit circle, so pi over 8 somewhere, it's half of pi over 4, it's somewhere down here, right? And actually I should be careful, it's not the unit circle this time, right? Because r is equal to 2, so it's a circle of radius 2. Then I rotate through 90 degrees, I get to my z1. I rotate through another 90 degrees, I get to my z2. Another 90 degrees, and I get to my z3. And again, everything is kind of nice and evenly spaced around the unit circle, and nice and symmetric, and you get this nice picture for the roots of a complex number. And this is a procedure that works in general.